So we have thermal physics, modeling a gas part 2, constant pressure process called isobaric process. In an isobaric process, pressure does not change. An example of an isobaric experiment, suppose we take a beaker that is filled with an ideal gas and stopper it with a gas-tight frictionless cork and a weight as shown. The weight F causes a pressure in the gas having a value given by P equals to a pressure formula, force over area, where area is the area of the cork in contact with the gas. You can see from the red highlight. If we now heat up the gas, it will expand against the cork, pushing it upward. Since the neither F, the force, nor A change, P remains constant. From the previous slide, pressure equals to force over area, and force equals to pressure times area. Based on our picture, that change in volume equals to area, cross-section area of the cork, times the displacement. Work done by the gas is just a force it exerts on a weighted cork times the displacement, x, it moves the cork. And the force is equals to pressure times area. So force equals to pressure times area. And then we can rearrange area times the displacement is change in volume. Now we have the new equation. Work done by expanding gas at a constant pressure equals to P times change in volume. If change in volume is larger than 0, gas expands, then work done is positive. If change in volume is less than 0, gas in this scenario gas contracts, then work done is negative. Shows that for an isolated ideal gas, volume proportional to temperature during an isobaric process. So we're going to use ideal gas equation, PV equals to nRT, then volume equals to nR divided by P times T. Isolated means N is constant. No gas is added to or lost from the system, so N is constant. Isobaric means pressure is constant. So N and P are constant. Of course, they are also constant. So V equals to nR over P times T. So nR over P is constant. That means volume proportional to temperature during isobaric process. Now let's take a look at isovolumetric process. Volume does not change. When the temperature rises and the pressure rises. And note that volume was kept constant in this experiment. Shows that for an isolated ideal gas, pressure proportional to temperature during an isovolumetric process. Ideal gas equation, rearrange. P equals to nR over V times T. For isolated means N is constant. No gas is added or lost from the system. Isovolumetric means that volume is constant. So N, V, and R are constant. So that means nR over V constant. That gives us pressure proportional to temperature during isovolumetric process. Isovolumetric, sometimes called isochoric. Constant temperature process called isothermal process. We have a graduated syringe which is filled with air, is placed in an ice bath and allowed to reach the temperature of the water. So we have P1, V1 equals to P2, V2, or P times V is constant. Record initial states after a weight. P1 equals to 15 and V1 equals to 10. and T1 equals to 0 degrees Celsius. And record the final after a wait. P2 is 30, V2 is 5, and T2 is 0. We keep the temperature constant. And we find that P1 V1 equals to 150, P2 V2 equals to 150. Therefore, P1 V1 equals to P2 V2 during isothermal process. Shows that for an isolated ideal gas, P1 V1 equals to P2 V2 during an isothermal process. From PV equals to nRT ideal gas equation, we can write P1 V1 equals to nRT1 and P2 V2 equals to nRT2. Isolated means N is constant. Isothermal means T is constant. Obviously, R is constant, so we have P1 V1 equals to nRT, which is equals to P2 V2, as N, R, T, all three are constant during isothermal process. In the PV graph shown, identify each process type as isobaric, isothermal, or isovolumetric, or isochoric. Isothermal, and we have different isothermal. So A to B, and then B to C, C to A. All right. A to B is isothermal, constant temperature. B to C, you can see from the graph, the pressure is constant, so isobaric. And C to A, you can see the volume is constant. That's the isochoric process. And the purple line shows all the three states changing. A fixed quantity of gas undergoes the cycle shown here. Find the work done during the process A to B. B, find the work done during the process B to C. We're going to utilize the work done formula. Work done equals to pressure times change in volume. From A to B. Look at from A to B. Change in volume is 0. Therefore, the work done is equals to 0. From B to C, final volume is 25. Initial value is 10. So change in value is 15. And we know the pressure, which is 8. And we utilize the work done formula. Work done equals to pressure 8, change in volume is 15, that is 120 joule, a positive value, as it is expanding. Find the work done during the process C to A. Observe that change in volume is a negative when going from C to A, as gas is contracting. And observe that pressure is not constant. So we cannot use W equals to P times delta V. But we are able to use work done equals to area under the pressure volume diagram. That is, area under the line is a trapezium. But we can divide that into triangle and rectangle. That is equals to, minus sign indicates change in volume is a negative when going from C to A and contracting. That's why it's negative sign. And area of the rectangle is 2 times 15 plus area of the triangle is 1 over 2 times 6 times 15. That gives us minus 75 joule. D. Find the work done during the cycle A, B, C, A. So we just total up the work done in each process. From A to B, no change in volume, so work done is 0. From B to C, pressure is constant, so pressure times change in volume, and the gas is expanding, so you get a positive 120 joule. And from C to A, gas is contracting. We can minus value, and that is area under the line. Cycle is 0 plus 120 minus 75 equals to plus 45 joule. Because W cycle is positive, 45, work is done on the external environment during each cycle. Now find total work done if the previous cycle is reversed. Then we want the cycle A, C, B, A to C. As gas is expanding, so we're gonna get a positive work done. And we can break down into rectangle and triangle. That equals to 2 times 15 plus triangle 1/2 times 6 times 15. That's plus 75. C to B, the pressure is constant, so we're gonna use P times delta V. Pressure is 8, volume is final 10 minus initial 25. That's negative 120 joule as the gas is contracting. For B to A, the volume is constant, or change in volume is 0, so we get a 0 joule. So cycle 75 minus 120 plus 0, that equals to minus 45 joule. Reversing the cycle, reverse the sign of the work. MCQ question: a fixed mass of an ideal gas is heated at constant volume. Which one of the following graph best shows the variation with the Celsius temperature T with pressure P of the gas? Fixed mass and constant volume means N and V are constant. Therefore, PV equals to nRT, and we can write P equals to nR our V times T. As our y-axis is P, our x-axis is temperature. And N is constant, R is constant, and the volume is constant. That gives us P equals to constant times T. It has to be a linear, so D is wrong. Since the temperature axis in degrees Celsius, and here pressure equals to constant times T, this T is in Kelvin. The horizontal intercept must be negative. Answer is A. So the graph below shows the variation with the absolute temperature T of the pressure P of the 1 mole of an ideal gas having a volume V. R is molar gas constant. Which one of the following is the best interpretation of the intercept on the temperature axis and gradient of the graph? A pressure versus temperature graph, when the temperature is in Kelvin or absolute temperature, P is directly proportional to temperature, or P equals to 0 at absolute 0. Based on ideal gas, PV equals to nRT, y-axis is pressure, x-axis temperature, we can rearrange. P equals to nR over V times T. And we know the mole number is 1. It says 1 mole. And based on that, the gradient equals to R over V. The correct answer is B. Average kinetic internal energy of an ideal gas. Since ideal gas have no intermolecular forces, the internal energy stored is completely as kinetic energy. So internal energy is a sum of the kinetic energy and the potential energy of the molecules. As ideal gas have no intermolecular forces, which means the potential energy equals to 0. Which means for ideal gas, internal energy is the kinetic energy. The individual molecules making of an ideal gas all travel at different speeds. The average kinetic energy of each ideal gas molecule has the following forms. This is the average kinetic energy of single gas molecule, which is equals to 3/2 times Kb, which is Boltzmann constant, times temperature in Kelvin, or 3 times R times temperature in Kelvin divided by 2 times Avogadro constant. Example: 2.5 mole of hydrogen gas is contained in a fixed volume of 1.25 cubic meter at a temperature of 175 degrees Celsius. A. What is the average kinetic energy of each atom? B. What is the total internal energy of the gas? First, what we're going to do is we need to convert the degrees Celsius into Kelvin. Temperature in Kelvin equals to 175 plus 273. That gives us 448 Kelvin. Now, let us find the average kinetic energy of each atom. That is 3/2 times Kb times T. And 3/2 and Kb, Boltzmann constant, 1.38 times 10 to minus 23 times temperature in Kelvin, 448. That gives us 9.27 times 10 to minus 21 joule. This is the average kinetic energy of each atom. Now B, what is the total internal energy of the gas? We just discussed internal energy is the sum of the kinetic and the potential energy of the molecules. For ideal gas, they have no intermolecular forces, which means the potential energy is 0. That means internal energy is the kinetic energy. So total internal energy is the total kinetic energy. And from mole number equals to N over Na, we get total number of gas equals to mole number times Avogadro constant. So the total number of hydrogen gas molecules are 2.5 times Avogadro constant 6.02 times 10 to 23. That gives us 1.51 times 10 to 24. Now, the total kinetic energy, which is the total internal energy, equals to N number of molecules times the energy of each one. So we have 1.51 times 10 to 24 atoms. Average kinetic energy of each one is 9.27 times 10 to minus 21 joule. That gives us 14,000 joule. C. What is the pressure of the gas at this temperature? We have converted the degrees Celsius in Kelvin. That is 175 plus 273 equals to 448 Kelvin. And use ideal gas equation, PV equals to nRT. Then pressure equals to nRT divided by V. The mole number is 2.5, R is 8.31, and the temperature in Kelvin 448, and divided by the volume 1.25. That gives us 7,450 Pascal.